Hello, good evening, everyone. Can you hear me?
Yes, ma'am.
All right. So we'll continue from where we left yesterday. So yesterday we had looked at our NumPy arrays, matrices, and some plottings. So today we'll continue from there, and we will look at some of the plots, and then we'll go into two of the algorithms in machine learning, which is PCA and k-means clustering. So, are all of you aware of PCA and k-means clustering? All right. So, okay, okay. I see a good number here. All right. So, okay. So we'll be doing those two algorithms today. If you are someone who have not yet studied k-means and PCA, maybe I will just explain what is the step, what are the steps here in those, and we'll do it. Later, you can, if you're interested, you can go back and see what the algorithms are. Please share the collab link. Okay, let me just, we want to do it here. We'll share it with you after the session. So you can open a collab and work along with me. We'll add in the same sheet that we had shared it today in the morning. We'll share it the day to collapse. All right. Okay, so let's start. So we saw yesterday the NumPy and matplotlib functions, right? So we'll just import it. So we will import NumPy as NP and matplotlib as .pyplot as PLT, right? So here the goal of this topic, sampling from distribution, bar plot, histogram, scatter plot, is we will learn how to randomly generate samples from certain distributions. Okay, so you would have seen various samples when you studied stats courses, or even if you studied, if you have studied both, gone through the ML courses, you would have come across many distributions like Bernoulli, normal, right? Uniform, and so on. So how do we generate those samples is what we will see today. So what do first is we will set our we'll use this RNG function, which is okay. So we'll set this. Uh, just give me a minute. Okay. All right. So let's import this. So now we'll use this function np.random.default.rng to generate the random numbers from various distributions. So this is what we are using. And we have set up here. We have set the C to be 42. You can use any number that you want. So this will make sure that the number that you are generating it produces the same number every time you run the code. All right. So very first distribution that we will see is for Bernoulli distribution. Like it's a very simple distribution, right? So what does Bernoulli distribution do? So the outcomes in the Bernoulli distribution looks like you have two kind of samples coming, right? One is either 0 or 1, right? So there will be some probability of success to it. Like what is the probability of success of getting ahead, getting a 1? So that is what you define your P to be, right? So you will have only set of two outcomes, 0 or 1, with certain probability. So in like how do we code this? So what do we want to do here? So we want to generate samples from Bernoulli distribution, right? So we'll use this RNG function, which is random number generators. It generates pseudo random numbers. Okay, so it appears to be like it's not entirely random, but it appears to be random. Okay, so we do RNG dot choice, right? So like if you look here, so what choices do we have for Bernoulli? So we have only two choices, right? We have either 0 or 1. So the 0 and 1. Now what we have to do is to also assign a probability to it, right? So what are the probabilities? So let's say we assign probability P to be 0.1. This is the probability for occurrence of 0. And then your probability of occurrence of 1 should be 0.9, right? Because both these probabilities should add up. So this is about how do we want to generate our samples. Now you have to mention the size. So we'll first do a size, a smaller size. So let's say the size we want is, let's say, 10, right? So you run this and let's just see what the samples look like. So you see the samples are 1, 1, 1, 1. There is just 1, 0 and remaining are all 1, which is aligning with the probabilities that we have set in, right? We had set the probability of 1 to be 0.9 and probability of 0 to be 0.1. And if you are generating samples of size 10, it actually, the sample that we got, it actually represent that. So you can increase the size, like it's not that you're going to get the same number of, like always the same number, but it will resemble the same probability, okay? So you are generating samples from the Bernoulli distribution with probability of success to be 0.9. So you can just keep on increasing the sample size and see how does it look like. So you will see either it is 0 or 1. So let's just change maybe probability of failure or probability of 0 to be, let's say, 0.4, right? Or let's say maybe 0.3 and 0.7. Okay? So you can see there are more ones in the sample than there are number of zeros here. So it actually represent this whatever probabilities we have set in. So you have more number of ones and you have more number of lesser number of zeros. Okay. Any doubt here?
Ma'am, what is RNG?
Just how you
RNG is,
initiate an RNG.
RNG is random number generator. So this function, this RNG is basically giving you the random numbers, it's generating the random number. And dot choice, so the choice that you have, so you are generating 0 and 1 with certain probabilities.
So are you, how are you importing this? Can you show the import
Sorry.
statement once?
Couldn't hear you. Can you repeat?
Can you show the import statement? How are you importing this RNG?
Import statement.
Ma'am, is this RNG basically a part of NumPy or you're importing it from Python itself?
No, it's a part of NumPy.
Oh, okay.
So NumPy has this, NumPy has this random function, right? And then random has this default RNG. Thing. You can check this part. Maybe if you hover over it, you can see. Can you see this? Default dot random dot default RNG, right? So it basically generates the random numbers.
Seed is for the reproduction, right?
Seed is for reproduction, yes.
And what is reproduction?
So like if you set the seed, like it will generate the same sample every time you run this code. So let's say if I have set the seed, like run this, and now let's maybe try this smaller sample.
Ma'am, can we keep a counter of 1 and 0 so that we can?
What?
Counting of ones and zeros in the sample.
Oh, okay. Can you see this? See, we had set the seed to be 42. And now if I run this, we are getting this array of 1, 1, 1, 1, 0, 1, 1, 0, 1, right? You have 2 zeros and just one I mean, remaining 8 ones.
So
You run
it
it
will
again,
not.
you get the same sequence. It will not change. You will get the same, once you set the seed, you are going to get the same numbers, same array you will get.
Ma'am.
Same proportion of numbers.
No, exactly same samples you get. So if you observe, maybe let's do 5, if to for better, let's do 5, okay? So we set the seed, and if you say this, what is the number you got? You got 1111
Four
0.
ones were starting.
I run it again.
So remember, what is the use of it? Means if
So-
we are not generating it randomly, what is its use? And why the parameter 42 is used exactly?
No, you can
Okay.
you can put any seed you want. So let's say
Maybe I can explain this part if you permit.
yeah, sure.
So basically, seed is used for reproducibility. So, for example, if you write a code on your for collab, and you have this random function, you have studied random in Python. So it will, for example, every time you run this function, it will generate different set of numbers, right? So suppose now you're writing a experiment or something like, and you have to reproduce it, say 5 days ago, run the same code. So, but because you have used this random function, and you want the same set of random numbers to be generated when you show the experiment to someone else. So we use seed for that, so that when we run this experiment, say to show it to someone else, the same set of values are generated, so it does not tinker with the results. Otherwise, what happens if we do not use the seed? It can generate some other numbers that time, and it can basically deviate the set of numbers generated, and results might not be actually the same. So it basically it's used in like machine learning. So
Basically,
I
it is
hope
in
you got the
debugging.
idea.
Like, when you do debug, if someone is having issue in your code and he will give you some number, he will say XYZ, and you cannot put the same random input number. So he will mention that he used seed that much. So you will also get the same amount, same input what he is getting, and then you can reproduce the error in your system, and then you can fix it, and you can debug it with the same input what he is getting.
So the 42 is any parameter.
Anything you can with 1500
any,
also.
you can maybe any number you put. Maybe let's say I put 1.
Okay.
So
So
it will still
it
work.
gets saved in the memory that this
So
random experiment had happened, and when someone
yes,
else will run it, so you should use
it
seed
will
one.
give the same sample, right? So if you see 11011, you will keep on getting the same sample every time you run this.
Ma'am,
So we
but
can think it of
before
we can think it of like we are using some Fibonacci series where we are initiating the first two numbers as per our requirements as per our scenes, right?
Can you repeat?
To get that same Fibonacci series, we are initiating the first two numbers in the same manner as per this seed, like this.
Means we're
You're
getting the
talking
same
about
experiment.
Fibonacci numbers.
Yes. If you change the first two numbers, then your Fibonacci can change, na? So if you are fixing those first two numbers, like the seeds we are fixing over here, we can generate the same set of random numbers afterwards whenever we use it.
Yes. Right.
So we are locking the randomness. Means.
ma'am, but before when you ran the code of choice, we got 4 ones and at last we got a 0.
4 ones. Okay. This here, right?
Yes, ma'am. So it doesn't follow the exact proportion, like you have mentioned 0.3 and
No.
0.7
It
here.
follows.
So
It doesn't
earlier
follow the
when
exact proportion. Like it
yes,
just see, probability of getting 1 is 1, but it did not be like exactly
exactly
because
that.
you're
Yes, it
generating the
can be around.
samples. Right?
Yeah, like if we go for 100 samples, it can generate
Yeah.
like
So higher the sample, the better the
67 zeros
accuracy
and
you might get. Yeah.
okay, yeah.
So it's not like that you're going to get the exact, but it will be almost similar.
Close to
Yes,
what
ma'am.
we
But
Close.
yeah.
Yes.
next time when you ran the code, all the numbers in array were one only, but seed was set still.
Mm-hmm. See, you can put any numbers here, doesn't matter.
Yes, ma'am. As you said, like the
Alright.
numbers will be same,
Which
but
numbers?
the random generated numbers, so the zeros and ones will be same exactly. But when you ran the code before, uh, 2 3 times to check, we got all ones, and the different positions were changed before.
Here, right? This
No,
one you're
Yes,
saying.
he's
ma'am.
talking about positions. Actually, positions can change, but the number of zeros
No, no.
and ones will remain the same.
No, no, actually,
Positions will also
positions
not
also
change.
not
It will
change.
not change. See,
Yeah,
it will not change. You look at it, positions are not changing, right? If here you have 0 at third and the 10th position. Every time I run this, I'm going to get the 0 and 0 at third and the 10th position.
but
You
when
can
you're running the
explore
next cell,
this.
no, ma'am, the different cell, the
Mhm.
positions are changing and the numbers were also changing.
Yeah, because see, here you had done it for this function. No? I mean, you're generating it here. Now you have to like set the seed again and then you can repeat.
Actually, when you are running the seed function, that range function, then in that in the above one, then it is showing only two. Uh, no, above one, above this.
Where? This one?
Yes, yes, ma'am. In this, ma'am, the size is 10 and the probability of 0 is 0.3, but it is showing only 2.
Yeah, exactly. So you're not going to get the. I mean, this is just random number that you're generating. It's not that it is going to give you the exact probabilities. The higher the sample size is, better the accuracy you're going to get. So, like for example, let's see here. So here we have generated samples from Bernoulli, but size is 10,000, right? So if you pick the size to be 10,000, and we'll see the bar plot how to do this. But you can see that the number of ones that you have is very close to 700, and the number of zeros that you have is very close to 300, right? So it kind of, I mean, the higher the sample sizes, the better. I mean, the probabilities P is going to be more closer and closer. Okay. So we'll share the collab. You can explore it.
Ma'am,
All
so
right.
what is
Let's
the way
move.
to keep the seed global? Is there any
Uh,
way to keep it global for any Jupyter Notebook collab? Like if you run different cells, then no use of seed.
okay. So, but see, here we are going to, in this collab, we are going to work on different samples, right? So you can like different distributions we are going to generate. So like in some way we have done it over here, like uh, but okay, let's just put it in here. It should give you the same samples. Let's just see. So we have set the seed. Let's run this one. This is what we work. Right? You run this again. So you have to put it in the same, like every time you have to run, I mean, generate samples, you have to assign the seed.
So it is useful only in file type code, not in cells.
Yeah, so every time you have to like set the seed and do it. I mean, whatever samples you are generating, you have to set it.
Ma'am, I just looked up like how to set the seed globally. Like if you, I think if you use np.random.seed right at the beginning, that will make like for any time you create a random number generator, it will use the same seed.
This is what you're saying.
Yes, yes, ma'am. And put just the value inside.
Okay.
Huh.
You can explore this part, setting the seed, right? You can explore this.
As far as I understand, the seed is
No, this still doesn't
already.
work.
It has to be global only because, like we use random state in the machine learning models. It never changes. It always whatever machine or whatever system you use it on, it remains the same. So the seed should also be global, just like that, as far as I can understand.
Ma'am,
Actually,
I got
here
the
I
solution.
don't think
It is
there is a
we
need
are
for.
writing.
Okay, let's just move forward, I would say, right now. So you can explore this part. I think it should have worked, but
Ma'am, because you set the global seed before random generator, that's why. So again, it became before like.
yeah, so that's why
You can remove the
earlier we
seed
had set
part
it.
in the.
That's why we had set it along with it, right? And it was
You
working
can
fine.
remove the seed part inside the default random generator number. It will work if you remove seed part of RNG.
Yeah, what did you say?
In
You
in
can
the default RNG, if we remove the seed.
This is what
now
you're
it
saying.
should work.
Let's try. Okay. No, right? Still not working.
Now we can proceed.
Okay, let's just move to the next part. We'll see if, what is going wrong here. Okay, so all right. So what we have done is we had generated samples from a Bernoulli distribution, and the sample size is 1,000. We have set the sample size to be 1,000. Now if we can check the shape, and the shape is 1,000, right? So you'll get an array of 1,000. So if you just do this, you get 1,000. Now to see, now we have certain number of samples which is coming, which is taking the value 0, certain number of sample which is taking the value 1. So we can say it on the bar plot. So for the bar plot, what function do we use is plt.bar is what we will use. So, but before that, what we also need is how many zeros that we have and how many ones that we have in the samples. So what we have done here is we have set initially 0 and 1 to be 0, 0, right? And for every time, like as I changes, if xi is 0, you update 0 to be 1, otherwise you update 1 to be 1. And when you look at the final 0, 1, it will give you the number of zeros and the number of ones in the sample. Okay, so the number of zeros that you had in the sample is 313. Number of ones that you had in the sample was 687. So now we get to the bar plot. So for the bar plot, like what do we need? So we need what all values we want, right? So plt.bar is the function that we use. And here you can see So you want the bars for 0 and 1, right? So you want the bars for 0 and 1. So you set the xy, so 0, 1, and this width that we have set it over here, just adjust the width of the bars that you get, right? So you can run this. Just first remove the. Okay, so this is how my plot currently looks like. Now, if let's say if we remove this part also. So here it just gives you 2 bars, one with 0, one with 1. But currently it is not indicating what is 0 and what is 1. So that's why we are using this BAT.xtext. So for the 0, it is giving me like it is giving me 0, and for 1, it is giving me 1. So now you can see here that now you can easily see that the smaller bar is for 0 and the bigger bar is for the 1. Okay. So if you want to adjust the width, we had the function earlier, so we can just write set the width. Maybe set the width to be 0.5. So it changes it to it makes it a little thin. That's all. So you can adjust the width if you want, but not very necessary. So this is how you can do the bar plot. Now, so far we have seen only the Bernoulli distribution. Now, if we have to generate samples from, let's say, normal distribution, so what we can do, we can so for the normal distribution, let's say we want to generate from normal with mean, let's say 1 and variance 4. Okay. So this is quite simple. So you will do just x equal to rng.normal. Right. So once you click on normal, you can see you want location, you want scale, and you want size. Right. You can see it over here. So for the normal distribution, I know there are 2 parameters. One is the location parameter, which is mean. And what is the mean that we want? We want the mean to be 1. So we set the mean to be 1. The variance, the standard deviation is what? The scale is given by standard deviation. So we put it 2. And how many samples do we want? Let's say we want 10 samples. Run this and we'll get 10 samples from a normal distribution. Right? So you can increase the size, you'll get more number of samples, but make sure this 2 here is the standard deviation, it's not the variance. Okay? So standard deviation. So once you have this, once you have the samples, like how can you visualize this normal distribution? You have a 10,000 sample. Here in this case, we have generated a sample of 10,000 samples from distribution with mean 1 and standard deviation 2, right? So it's a continuous distribution. So what can you do for this? You can plot a histogram. So again, plotting histogram is quite easy. So just in case of bar plot, we have to just do plt.bar and put the values. Similarly, here also we can do the same thing. So we have to do plt.hist, right? And what do we want? We want to plot a histogram of x. So once we do it, so currently, okay, I think we have not run this cell. Okay. So this is how it looks. Okay. So we have 10,000 samples coming from a normal distribution with mean 1 and variance 2. And if you look at histogram, you can see that the mean, this histogram is centered around 1, right? So the mean is 1, the location is 1. Okay? So, but you can also make some changes, like clearly this pen size is not given, or all the pens that is not like clearly differentiated, right? So few additional things you can add. You can give how many pen size you want. You can give, or you can also draw the edges. So to specify the pens, what is the number of pen size you want, you can give that, and that is going to be 100. Okay. So we have taken it to be 100 because see, the sample size is quite large. It is 10,000. So if you take lesser number of pens, each pens are going to look very narrow, right? So that's what we want to avoid. So let's take the pen size to be 100, and edge color is black, and this is going to make sure that each pens are clearly differentiated, uh, right? So let's just see how it looks if we take the pen size to be 100. So this is how it correctly looks like. Still, it is quite thin, right? The pens are quite thin. When we had not specified what is the pen size we want, it is kind of giving us a better bucket for the histogram. But let's just say I just change it to 1,000 because we have some 10,000 samples. So that should look better. Let's go. So we have this normal distribution. Oh, sorry. We have to reduce it, right? So we have now made it 10 buckets. I hope this is okay. Any doubts so far? All right.
I guess normal distribution with lesser bins is a binomial distribution, kind of a.
What?
I guess normal distribution with lesser bins kind of a resembles binomial distribution.
Yeah, I
Because
mean,
the graph,
like any distributions, is DLT, right? So as the sample size increases, any distribution is going to uh, be kind of normally distributed from CMT.
but just one question, ma'am. Is it always that we like represent normal distribution in form of histogram, or we can also simply plot a curve as well?
You can also plot a curve as well. Not a problem. I mean, you're talking about PDF, drawing a PDF, right?
Yeah, usually when we represent normal distribution, it's a curve, right? But here we are representing them as
So
histograms. But we
we
can,
are just showing, we are just showing here that like all the samples that we had, what kind of shape it takes. So the more the pen size we had taken, it kind of giving us a better bell-shaped curve, right?
yeah.
So let's see this 500. So yeah, it kind of it will give you a better, more visibility will be there for bell-shaped curve. Okay. Next is our bivariate Gaussian. So this is very similar to your normal distribution. It's the only difference here is that now we are talking about this normal distribution in 2 dimension. Okay? So now you have two random variables, and they are jointly distributed as bivariate Gaussian with mean 1, 2 and covariance matrix 1, 0, 0, 5. Okay. So for bivariate Gaussian, what the function that we can use is, so x is equal to RNG dot. Now this is multivariate. This is no longer single variable. Now we have multivariate, and in multivariate we have you can see various options: multivariate, hypergeometric, multivariate normal. So what we want is multivariate normal, right? So again, once you have this multivariate normal, what are the things that you have to specify here? You have to specify the mean, you have to specify the variance, and you have to specify the sample size, right? So in this case, your mean is no longer a number here, right? Now it's an array, right? It's going to be a 1x2 matrix. It's for 2 dimension, so it's going to be an array for you. So now you have to specify your mean. So in this case, we have taken mean to be. So let's take mean to be 1, 2, right? So mean is np dot array 1, 2, and my covariance matrix covariance is just 1005. So that also we can write here. So np dot array. What do you want? We want a matrix. So we can just the number. So it's 10 and 05. So if considering this is the mean, and like if you want to generate samples from a mean with mean 1, 2 and covariance 1005, then these are the parameters that you need to put in over here, right? So, here. So what do we want? We want this to be new with covariance matrix C, and we need to specify how many samples we want. So let's just say first we want 10 samples to fit. Okay. So if you click X, you can see here that you have 10 samples now and coming from. So first sample is 0, 3, this, right? Second is this, third is this. You got 10 samples from a bivariate normal distribution with mean 1, 2 and covariance 1005. Right? So similarly, this thing has been done for 1,000. You are generating 1,000 samples here, and we are taking the transpose, right? So while we're taking the transpose, you can see that in this case, like when we are generating 10 sample size, in this case, we are not taking the transpose, and currently the shape of the matrix that we have is N cross T, right? But if you have looked at, if you have already studied MLT, you would have seen we are all everywhere we are considering X to be a D cross N matrix, right? And D is the number of features and N is the number of data points. So we want to convert this X to D cross N size. So what do we do here? We just take the transpose of this, just to transpose, right? So once we did the transpose, now we can see that this is this is of the size D cross N, that is 2 cross N, right? So that is what we number. Yes.
Ma'am, before we did transpose, there were two values in each row.
There were two values in each row. Wait, before we did the transpose here, right?
Yes, ma'am.
So now, see, in each row there are two values, right? So this is one data point. This is another data point, right? This is another data point, third data point. This is how you see. This is the fourth data point. Why there are two entries here? Because one is from the X, one is from the Y. It's a bivariate normal distribution we're talking about, right? So once currently this the size, if you look at the size of this or the dimension of this, it is giving you N cross P, right? This is 10 cross 2 is the size, but we want to convert this to D cross N for our like in MLT course we have used it as D cross N, so we want to stick to those notations, and that's why we are just doing the transpose. So once we have done the transpose, now I can see it is D cross N. This matrix now is of D cross N, which is 2 cross 10, and that is what we wanted. So that's about the bivariate normal distribution. So let's just run this, and we can see.
Why we did the transpose actually?
We did the transpose to make it to D cross N instead of N cross D. Because if you have done the MLT course, you would have seen X we have taken as D.
Okay, D cross N you wanted. Okay.
That's the only reason. So all the calculation would be easier for us because we are following those notations. All right. So this is how the samples looks like for bivariate normal. Now, if we want to visualize this, like how the samples look like, we can do the scatter plot. All right. So for scatter plot, again, it's just very simple. So what we do is you just do plt dot scatter, and now here you want your the first component and you want your y. So if you look at x, I'll just take a smaller example. So if you look at this x, so x0, right? X0 is going to give you the first dimension, and x1 is going to give you the second dimension, right? So we'll just do that. So you want all the rows and you want x of 1. So this should for, yeah. You see, this is how currently my scatter plot is looking. But what difference? I mean, there is some issue over here. Is that there's a scaling issue that we get. So if you see, my variance for the second variable is given to be 5, and the variance for the first variable is 1. But this is not what the figure is giving us, right? It's kind of saying it's almost like along both the axes, the variability is similar. So to avoid that, what we will do is we will set this axis to be equal. So that will make sure the scaling is right. That's what we have done in here. So what we have done is we just put axis to be equal. All right. So if you put axis to be equal, now you see that you can see that this is how my data set looks like, not what we saw here. Okay. So there is more variability along the y-axis or the second axis. And these lines that you see just to denote the axis, and that is given by plt dot x line, xh line. So h for horizontal and e for vertical, and this is just going to give you the axis plt dot x line, plt dot xb line. You can change the line style if you want. You can change the line width if you want. Right? You can play around with it.
Madam, how will this understanding help, madam, that it is more variate in y-axis?
See, I mean, this is if you just plotted this, if you just did this, like for this data set that we have run, this data set, right? We wanted to see how the data set looks like, and for that we did the plotting. We did the scatter plot, right? But is this how my actual data is? No, right? My actual data set actually looks like this. Okay. So we just want to make sure that what the data set is, it should actually resemble the correct plot, and that's why we need to set this axis to be equal. AC dot axis to be equal. So you see that all, like moving forward, all the scatter plot that we're going to plot, we'll always set this axis to be equal. Okay.
Okay.
So next is about the sample covariance matrix. We'll just quickly do this. Okay. So all of you, I mean, when we were doing the sampling from the bivariate normal, we set the covariance matrix. Like we used, I mean, this is the population covariance is what we have set, right? So we are generating the samples with mean 1, 2, and the covariance matrix 1, 0, 0, 5. So this is my population covariance. But the samples that you have obtained, so this sample that you have obtained, the 10,000 sample, 1,000 sample that you have obtained, this is from the covariance, I mean this covariance matrix, right? This covariance. But once you have the data set, how can you find the covariance, right? So for that, we all know the formula, right? What is the formula for covariance? Finding the covariance, it is XX transpose, right? XX transpose divided by n is what we do, right? So we'll see that. So what we have specified here is d cross n, d comma n is my x dot shape, which is in this case was uh, 2 cross 1000, right? This was my data set that we had taken. Now, currently, let's see. So, there is the mean. So, if you just run this,
Madam, I was trying the same code in my system, but I did not get that shape. I was having the same shape. I just got the
yeah,
line.
see, the samples that you would have obtained is different. It's going to be different, no?
But the shape didn't change even a bit after
Even
adding
a
those
bit.
lineage, XH line and XV line.
I mean, you got the same shape.
No, I did not get this shape. I
Yeah, because
I got
your
some other
samples are
shape.
different. Your samples are different, right?
I got some other shape previously, and after adding those two lines also, I am getting the same shape along with those
Did
two
you
lines.
use the same covariance?
Yes.
Then you will get you should get this, right? Maybe some points here there, but kind of this is the shape you should get.
Yeah, I don't know. Maybe.
Right? I mean, if you're drawing samples from mean 1, 2 and the same covariance, some data
Mu
points
is
may be
1,
different,
2,
but
and C is 1005.
mu is 1, 2 and the C is 1005.
1005.
So depending on, I mean, some points, some samples may be different, but you're drawing a very large sample size, right? So if you instead of doing 10,000 or 1,000, if you just do 10, let's say, then you will see the shape is, you'll get different points.
Acha.
Since a larger size, I mean, you will get a similar kind of shape.
Plot dot axis equal.
All right. Thanks, sir. Just for visuals. Yeah, I mean, these lines are for axis. So these lines are axis. Yeah, we just plotted the axis. All right. Okay. So we were here. This is my mu, and what is this mu? Mu is the mean, and it is 1, 2, right? But if you look at this covariance matrix, C, so just take that also. So now the C is your 2 cross 2 and U is just one array weight, right? So, but for finding the covariance matrix, we need to center my data set. Okay. And how do we center it? We take my data set and we subtract the mean, right? So that is what gives me the center data set. Now I know that my covariance matrix is actually, so my covariance matrix, covariance matrix is XX transpose divided by n is what we have, where x is centered. Where x is centered. So first, I mean, the data set that we had obtained here is not centered. I mean, first we need to center this data set. Okay. So to center the data set, we need to subtract my mu from x, right? So that's why that's what we are doing it over here. But to subtract x from mu, I need to first change the shape of, or we need to convert this mu to a column vector, right? Currently it's an array, right? And C is your matrix. So you need to convert this to a column vector to the for subtracting this, right? So that's why if you see, we are doing mu to be x dot mean, that is going to give the mean of data point, and axis is equal to 1 is giving what? It is along the columns. So all the data point that you have, you add it along the columns, and then that is going to be the mean. So what we are doing is, so your mu, this is not the mu that we had specified. This is the different, this is the mean that we are finding from the samples obtained. Okay, there's a difference. So maybe let's just call mu s. This is just to be known, this is from sample. So how do we find the mean of the of a data point, data set? I will just do x dot
But
or
how
np dot mean of x. Yeah.
How it is different, because we have generated a sample around that mu only, no?
No, you have used that mu to generate the sample. But now once you have the sample, your mu might vary a little, right? I mean, you're not going to get the same mean to which you have generated.
Okay.
Right. Like for example, you have generated samples from, let's say, a Bernoulli binomial Bernoulli distribution. But once you have taken the sample, like in the when we first started the Bernoulli example, we saw that even though we were generating samples from p.7, the samples that we got, let's say there was only 2 zeros. So from there, the sample mean that we got was 0.8, but actually it should have been 0.7 because we generated samples from there. So it's not that you're going to, once you have those the parameters which used to generate the sample, you're not going to get the same value of those parameters from samples, right? But as the sample size keep on increasing, it will slowly give you, I mean, it will approach towards the same value, like your weak law of large number. Okay, so mu is np dot mean, right? Or mean of what? I am trying to find the mean of x, and my x is the is a data set of size 2 cross I think 1000 is what we are taking. And now we want to find its mean along the axis is equal to 1. Right? Why axis is equal to 1? Because we want to find like add all the components along the columns. So that's why axis is equal to 1. So if you run this, let's see, it's called new. We get this 0.09. This is the mean that we got. But this is not equal to 1, 2, but very close to 1, 2. Now, what if I want to know the shape of this? This is an array of size 2, right? I mean, this is just an array. Now, if I have to subtract this mu from this data set X, I need to first convert this to D cross 1 size. So that's what we'll do here. So what we will do is we'll do reshape. So, in PC, we are going to use this quite a lot. Oh, sorry. For reshape, we want to do it as D cross 1. Okay? And in this case, my D is 2. Right? 2. Now, if I call my mu, this is this. Right? So now we can subtract. So what we have done, you have your C, which is xx transpose divided by n. Now instead of x, you have x minus mu. And since this is a dot product, so that's why we have used add the rate. Okay? This will give you the inner product. And we can run this and we'll get our. So this is giving me my sample mean and this is giving me my sample covariance. This is my sample covariance. Sample covariance. Now, if you want to check like how close these two are, the population variance and the sample variance, sample covariance and population covariance, they can use this this command for the norm to check what's the difference. So this is currently 0.30. So now if you increase the sample size, you should get a smaller difference. Let's just see this. So maybe let's do it 10,000. Then we got needed. Let's just see. So it's you know, you see, like there are more. It's more closely packed as we do sample size. And display. So now this is, if you look at the difference, it should be less, right? It reduced. Or it was something else. Now it has reduced much lesser. So as the sample size increases, this difference that you get is going to reduce. So that was about finding the covariance for any matrix, finding the covariance matrix for any data set is what we looked at. Now we are going to use this in PCS. So just before that, let's just see one more thing, which is GMM. So this is Gaussian mixture model. So, all right. So in Gaussian mixture model, what do? We have this. So, like, what are we saying here? In Gaussian mixture model, your samples, your data set that you have, it is now coming from a set of different normal distribution. So maybe let's say it's coming from bivariate or a set of 2 normal or a set of 3 normals, right? So now the samples are coming from different normal distributions. So given that, I mean, if we want to generate samples from Gaussian mixture model, how can we do it? So the very first thing is we will have to assign what is if you have, let's say I'm taking 3 mixture model, okay? So I have to have some probability with which the samples are coming from, let's say from the first component, from the second component, and from the third component. Okay, so we'll assign the probabilities. Let's say for the first component, we assign the probability to be 0.2. Like with 0.2 probability, my samples are being generated from the first normal distribution. With 0.3 probability, my samples are generated from this normal distribution, and with 0.5 probability, my samples are being generated from the third normal distribution. And the means that we have specified at 0, 5, 10. So we are saying the first normal has been 0, the second normal has mean 5, the third normal has mean 10. And we are assuming that the standard deviation is same for all of these distribution, which is 1. Okay. So considering these conditions that now we are going to generate samples from mixture of 3 Gaussians, right? Which is with mean where the first normal is with mean 0, 1, second is from mean 5, 1, third is from mean 10, 1. All right, and these are the probabilities that we have assigned. So we first need to decide. We first need to generate from these. Like we need to first decide which indices we are going to choose. So you have now 10,000. Okay. So we want to generate 10,000 samples. Okay, and now since we have a mixture of 3 Gaussian, so we have to choose from 0, 1, 2. So remember, like when we had when we were doing the Bernoulli, we had 2 choices. We had 0 and 1, right? So there we had done RNG dot choice, and we had specified just two values, 0 and 1, and with certain probabilities, right? We had given the probabilities and specified the size. So, but now in this case, what we have is we need to, like we have three components now. So now we have 0, 1, 2. So instead of just 0, 1, I need to have three components. So 0, 1, 2, and certain probabilities. And the probabilities we wanted was 0.2, 0.3, 0.5. Okay. So let's assign the probabilities 0.2, 0.3, and 0.5. And what is the size we want? Let's just say size we want is 10. It's 10,000, 1,000. 1,000. Size is 1,000. What we want. Now, so what this is giving is now what did it give? It gave you 1, 1, 1, 2, 1, 1, 0, 1, 0, 1, and it kinds of resemble actually not. I mean, okay, it should have more too because probability is 0.5. But okay, this is a sample that we got. And now you can see there are more twos because okay, ideally we would want that because it has the highest probability. So this is what it generates, right? So now what we want is, once we have this, what we would want is that for every, now we need to generate samples, right? So if we have to generate samples, and we have to generate sample of size n, okay? So, and these samples are going to come from a normal distribution, correct? So these and how do you generate samples from normal distribution? You do RNG dot normal, right? And with some mu, and in this case we want the variance to be 1. So we'll just assign that, and you also need to give some size, right? But now here, what we would want is that, let's say the first sample that we have, it should come from my first, I mean, this component of mean, right? So it should generate, the first sample should go to mean, it should be generated from normal with mean 5 and variance 1, right? So we'll just put it in this for loop, and we'll get a sample. So that's what we're doing here. You have this for first we are just creating an empty a set of an array with all the values to be 0, and for every I that we take, it's going to give you the mean with mu, which is the index for this compile, right? And like as I said before, so here the first, if the very first value you're getting is 2, it means for I is equal to 0, you are going to create the generate the sample from mean 2 and variance 1. Okay, and it will just keep on repeating, and it will update your x, right? So you can see the x you want. Large number, but yeah, so this is what it generates. So you will have x dot shape, you will have 10,000 or 100,000 an array of which takes 100,000 values. Right? So this is how we can generate samples from a multivariate, not a multivariate, it's a Gaussian mixture model. Okay. So to visualize this, we can just plot the histogram.
Ma'am, but in problem statement, mu is different than static.
Yeah, tell me what. Tell me again. In problem statement.
Yes, ma'am. In problem statement, mean is different, and we are taking
Okay. Yeah,
coding.
so
We
let's
are
just
taking
write that.
minus 10, 0, 10.
Okay.
Yes,
Let's
ma'am.
take 0, 5, 10. Okay. So if you take 0, 5, 10, just take this. Yeah. This is my B, right? So 0, 5, 10. All right. So now it will, if xi is, if the first component is 1, it will generate sample from mean 5, variance 1. If I is, if it is 0, it will generate from mean 0. If it is 2, it is generate from mean 10. Okay, let's just run this. Right. Now if we create the histogram, plot the histogram, now you will see there are 3 centers. So one is 0, one is 5, and another is 10. Right? That's how it looks like. Might have to call it first. Okay, so this was about the plotting, but this covariance is something that we are going to use a lot. Okay, so we'll keep on seeing this. Let's just start with PCA now.
Ma'am,
How many notebooks do we cover today, ma'am?
Yeah, we need to cover 2 more. Let's just see how much is possible.
ma'am,
Yes. Tell me.
just one doubt. When we are verifying the random numbers covariance matrix, that time we had assigned the uh, covariance for both as 0, the diagonal values, anti-diagonal, I
Right.
mean.
Other diagonal, right? Yeah.
Yes, ma'am. But when we checked for the random numbers we generated, it is coming minus 1.6, and next time we created the increasing sample size, we got greater than 0. We got 4, I guess.
No, it is not possible that you get it greater than 0. Um, okay, no. So there you see it had e, something of e, right? Exponent. So 10 to the power minus 4 it goes. So it is much closer to 0. Earlier you had a slightly bigger number, but when you increase the sample size, this became more closer to 0. I
Excuse
think
me,
you
ma'am.
missed the e part over there.
Your screen is not visible actually. It is in one place. Principal component analysis.
Yeah, I changed my screen. Okay, if you want to see that.
So there is an E over there. So telling that 10 power minus.
Yeah. So this one, right? So, uh, okay. Back to the data set. So we had generated this one, right? So see, let me just first 200. Okay. So with 100, if I want to estimate this, so it is 0.3 currently. Okay. Now let's just increase the sample size. Increase the sample size to 1000. What do you have here? This one. Now it is 0.03, right? Now you further increase. Increase it to 10,000. Yeah, this one. What happened? Now it is 0.02, right? Now if you want to increase it further, let's see. You can just check this. We'll share this collab with you. You can just try it with different values, and you can also other features if you want to add, you can add it and see. Now it is 0.005. So it is slowly decreasing, right? As the sample size is increasing, this is slowly decreasing. Okay.
Yes, ma'am.
All right. So now we will look at. Are you able to see the screen, ECL?
No, ma'am.
Okay. Is it visible now?
Yes,
Yes,
ma'am.
ma'am.
Visible.
So, all right. So, what are we doing in PCA? Like, what are the steps involved? If you know. So, the very first thing is we need to have a data set of. We want the data set to be the size 3 cross n, where d is a number of features and n is the total sample size. And once we have this data set, we want to center that so that we can find this covariance matrix, right? We want to center the data set, we find the covariance matrix, and then we find for the covariance matrix, we want to find the principal components, right? And to find the principal components, we need the eigenvalues and the eigenvectors of the covariance matrix, right? And the eigenvector corresponding to the largest eigenvalue is what gives me the first principal component, right? And the second one will give me the second principal component, and so on. So we will see this all this process over here. So the very first thing we need to do is to like import these libraries, NumPy and Matplotlib. And since we'll be generating numbers, so we'll import this, we'll run this random.default RNG also. So as I said, the very first thing that we will need is to generate samples, right? So we'll be generating samples from a bivariate normal distribution. So we have already seen how to generate samples from a bivariate distribution. And what was that? It was you do x2b RNG dot multivariate, right? You want to multivariate, you define your mean, you define your covariance, and you define your size. Right? This is what we do. Right? So for that, we need to specify my mean, my variance, and the size. Let's just say size we want to be 10. Now, not 10 is being 1000. Okay? So mean is something that you need an array, right? So let's take this mean and covariance is this is mean and covariance. So we are generating a sample of size 1000 with mean from a bivariate normal distribution with mean mu, covariance is this, and size is n. Okay. So this we have already seen. Okay. Now we run this, we got the sample. Right? So if you want to check the shape of this, we got 1000 rows and 2 columns, basically 2 features, because I mean you have the samples in 2 dimension. So number of features you have is 2, and you are generating 1000 data point. But now again, we want, as I said, we want our x to be in uh, is of the shape d comma n, d cross n, right? So we need to reshape this. So we need to reshape this. We want to reshape this to 1000, so 2 comma 1000, d comma n. So that's what we have done here.
Why is it?
In again the same reasoning that we want this in uh, we want the dimension of my data set to be t cross n and not n cross t. Earlier, what? Sorry, not reshape, transpose dot t. So earlier, the shape was 1000, 2, right? And 1000, 2 is of the shape uh, n cross t, right? X is n cross t. But now this will give t cross n, right? 2 cross 2 comma 1000. Okay. Same thing that we had done earlier. Now, since we'll be using this quite a lot, so we just put this in the function, and we have just put this in function. So if every time we have to like generate sample from the bivariate normal, we can just call this function generate and we can do it. So let's just skip this part. Just run this. Now, what is the next thing that you want to see? You have the data set with you. Now you want to see how does the data set look like, right? So what had we seen? Like we will do plot, we'll do plt dot plot, and we want here scatter. Scatter plot, and this is x of first component and x of second component, second row as well. And we want to set the axis to be equal. Gt dot axis. So currently, this is how my data set looks like. Okay. So what do we want to do? We want to center this data set. This is not centered, right? You just plot plt dot next time. Then it will be here. So this is how currently my data set looks like currently. Okay. So remember, like currently we only have the data set of the size d cross n. What is the next thing that we would want to do? We would want to center this data set. And as I said before earlier, that how do we center the data set? We subtract your x from mean.
Mu.
So now in this case, what will you do? You will do next is what? Next is center the data set, right? So to center the data set, you want to do x minus mu. But again, mu is an array. So you need to reshape your mu, right? So currently mu is this. So mu is 2 comma 5. It's an array. So you need to reshape this. So you will reshape. Maybe we can do. Let's start down. Okay. So how will you find the mean? Mean was np dot mean of x, and along the axis is equal to 1 because you want it along the columns, and this will give you the mean, right? You have the mean, now you want to do x minus mu. If you do x minus mu, you might get an error here, right? Because it's an array and this is a matrix here. So we need to reshape this. So we'll reshape this to 2 comma 1. So now it should work. So now you're getting uh, the center data set is what you have right now. Yeah. So if you want to visualize this again center data set, you can just do again the same plot you can use. You can just do the scatter plot. So okay, wait. Press the see what we had done here, which I skipped, is like we had also like kind of defined this function plot x so that we don't have to repeat this again. So one function that we had defined was this generate mu comma covariance comma n, which is like every time we call this function, we can generate the sample from bivalent normal. Similarly, for the plotting, we have defined this function x, and you can see that if you call this function x now, and I have not run this, so after you enter the data set, uh, we can run this, we can just call this function plot, and we get the plot for both the original data set that we had and the center data set that we had. Just skipping these parts on two ways. So you can see side by side that this is my original data set, and after we centered it, this is what my data set looks like. Do you have any difficulty in understanding this? You tell me, you can just go to the code. Otherwise, I'll skip.
No doubt.
Just ma'am, you're going so too fast.
I moved too fast. Okay, got it. Okay, let's just see.
Because
Okay, I'll try to complete.
see the code now, you scroll it up, so it is hard to go through the things.
No, but time is less, so let's just see what we can cover today. Then have to do it tomorrow. Okay, so I'll just tell you what I have done here. So, see, the very first thing that we did is to generate the data set. Generate the data set from bivariate normal distribution. Okay, and for this, we have defined a function. Defining a function generate with some parameters. It has three parameters. So once we have this data set with us, we can see how the data set look like. So just visualize the data set. Then what is the next thing? What we have done? After this, we try to center this data set because for PC we need a center data set. So we did centering the data set. Okay. And at the end, we did we saw how visualize the center data set. These are the four. Visualize the centered data set. Okay. So these are the four things we have done. I hope no doubt in this part, generating the data set. Okay, all right. So no doubt here. I would assume that no doubt given here as well. Plotting, I mean, seeing the original one, right? Okay, is also fine. So let's just use this on moving. by default, it is taking the color blue, and because I've not assigned anything here. But this is just to show. Okay, I think I had done already. So to show the centered one. Okay, this is currently how my data set is. Now, what do we want? We want to center this. Right? The third step is centering. So to center the data set, let's come down. Let's see this separately. See, as I said, we want to find the mean first. Okay, so the mean can be found by x dot mean axis equal to 1. Right? We had seen this as well earlier. Okay. Now what we want to subtract x from mu. But this we want to reshape is to 2, 1 because we saw it cannot be broadcasted. I hope you had studied this broadcasting method yesterday. Right? So that's why we need to reshape this, and this function now will give me every time I call this function center x, this will give me center data set. Okay. Now this is the center data set that we have now. So
just these
what
two parameters, 2, 1. How did you visualize this? 2 and 1 only.
Why 2, 1 is because see, you have mu in you have data set in what dimension? If you have to see, let's just print x dot shape, right? X dot shape is what? Sorry, there's no brackets. 2, 1000. Right? So it is, and it is of the shape t cross n. Right? So t is 2, right? So number of features is 2, and you have 1000 data point. And similarly, my mu is 2 cross 1 now. Like it has to be 2 cross 1. Earlier, what was the mean? If you go back to the traditional data set, here, you run this, right? If I want to know what is the shape of mu, right? Dot shape, what will it give? It is 2, 1. I mean, just an array, right? It will just give an array 2, 5. Right? So if you have to subtract your mu from x, you need to reshape this. You need to convert this to a column vector, right? Okay. So to convert this to column vector, we are doing this reshaping here, which is this is done. Yeah. So that's why we are reshaping this to 2, 1, so that we can subtract my mu from x. Okay. So now this is a function that we have defined for centering the data set. Okay. So you have the mean, you have the x, and what will it return? It will return centered data set. Okay. So once you have the center data set, what you would want now, you would want to visualize this center data set, right? So to see like the original, now if you want to see the center data set, what will you do? You will do plt dot scatter, right? You will do a scatter plot, and again, what you want? You want x, the first row, and all columns, and x and you want with this second row, okay? Second row, all the columns. Okay. You want to make sure that axis is equal, so plt dot axis is equal, okay. And you can do plt dot x, which line, not this, plt dot x b line. And there is also in scatter plot, there is something called parameter alpha, which makes sure how much opacity you want for a data point. So we can set this to maybe 0.4. Right? So let's just see this now. Once you have centered the data set, how it looks like. I think it has not run this. let's just run this working again. Okay. So this is my data set. Now this is the shape of the original data set. Right? This is not centered currently. Now what we did, we are centering this. Right? So we are centering this, and now if we plot this, okay, we have not called this function, that's why it's not doing that. Let's just down the function b. Yeah, see. So now what it has done, it has centered the data set. Right? Is it okay? So till here it is fine. Are you able to see like how can you do this? Okay, all right. So this is still centering my data point and visualizing it. Now, what is the next step that we will do? So just those. Yeah, till here we are done. Okay. So once we have centered the data set, my next step is to find the covariance matrix. Once we have find the covariance matrix, we will need to find
Eigenvalues and vectors.
eigenvalue and eigenvector. Right? This is what we need to do. So how will you find the covariance matrix? To find the covariance matrix, we need to do x transpose divided by n. Right? So what is my C? C is x. Now this x is my center data set. Right? We had done it before this. So x at this is to know the dot product, x transpose, right, x dot t, and divided by n. This is my covariance matrix. If I call this is a covariance matrix I get. All right. So we can find the covariance matrix for this center data set. Now, once we have this covariance matrix, next what we want is to find the eigenvalues and the eigenvector. Pencil. You want to find the eigenvalues and eigenvector. So how do you find the eigenvalues and eigenvector? I can do define eigenval, vector, right? And np dot
EIGH.
linear algebra.
Linear algebra EIGH.
Algebra dot EIGH. Right? Of you want for this, you want this for matrix C, right? You can call this algebra like vec and see what it gives you. So now you can see that you have the first eigenvalue for the covariance matrix is 0.1 and the second eigenvalue is 1.886. Okay. And the eigenvector is 0.70, minus 0.70, 0.70 and 0.70, 0.70 are the eigenvectors corresponding to these eigenvalues. All right, this is okay.
So second is the first PCA.
Second, for the eigenvalue 0.10, the eigenvector is minus 0.70, 0.70. Okay. For the eigenvalue 1.88, the eigenvector you have is 0.70, 0.70.
And that is PCA1, right?
That is PCA1, correct. Okay. So once you have this, now we can find out I can easily say that my PC principal component 1 is 0.70, 0.70 and PC2 is minus 0.70. 0.70. Okay. So this is about finding the eigenvalues and eigenvectors. So that's what we have done in these. So this is covariance, and we have defined a function here basically. Okay, so what we are doing is that see we need the first principal component and the second principal component, right? So when we are you see here, uh, when you have this, when you found the eigenvalue and eigenvector, what you have is 0.10 and 1.8. It is an ascending order, right? Eigenvalues are given in ascending order. So now let's just flip this. So when we flip this, my 1 point, it will give me in descending order. So what you can do is just to see. So I val is equal to I val dot flip. You flip this. Um, so the flip or
Ma'am, it's a
okay, you got
function,
it.
so brackets.
NP dot. No, it's NP dot flip. Here. So we want NP dot flip. So if you call this I should see change. So initially it was 0.10, but now you have 1.88, right? So when you flip this, you have now 1.88 and 0.10. Same thing, let's try for eigenvector. So because we want, like if you have flipped the eigenvalue, you also want the corresponding eigenvectors for the eigenvalues, right? So we'll do eigenvec. So this is NP dot flip. Want to flip what? Want to flip this eigenvec. But now, along which axis do we want? We want to flip the. We want to do it across the rows. Oh, sorry, columns. We want. No, rows. We want. See, axis is equal to 1 if we do. Yeah, yeah. So this, okay. Yeah, this is fine.
Ma'am, I
So
think
now
0 is correct, not 1.
no, 1 is correct. You can see here, right? Earlier for 1.88, my eigenvector was 0.706 and 0.707.
Ah,
Now
okay,
you
okay,
see
got it. Okay,
706, 707, right? Because
got it.
axis equal to 1 means you are flipping, you want along the column. When you do axis equal to 0, it means you want it along the row. It should be wrong.
Got it now.
So we'll flip this, okay? So now these are my updated eigenvalue and eigenvector. That's what we are doing here. So inside this getPC function, we have this eigenvalue, we have this eigenvector, and this is going to return me eigenval, and eigenvector. Let's see. Shashwat, may you have any question?
Ma'am, in the previous cell, you're saying eigenvectors for 1.88 are the second elements of both eigenvector.
This part.
In the previous cell.
Yeah. Here, right? This one you are
Yes,
seeing,
ma'am.
right?
So here eigenvector for 1.88 eigenvalue, it should be the second element of that array, right?
No, it is not second element of the array. It is this one 0.70 and 0.7 these two.
It's a matrix, so it is a second column, or
No, it's a second column. It's a second column is what you will get.
so second column is for the second eigenvalue.
Second
First column for
eigenvalue.
first eigenvalue.
First eigenvalue.
Okay.
Okay. So, all right. What we have done is we have flipped the eigenvalues and eigenvectors. Once we have done that, yeah. So, also whatever we have done so far, like finding the eigenvalue, flipping it down the axis, right? We are putting this under this function get PC. Okay, so if we call this get PC function, it should give me it should return me eigenvalue and eigenvector. All right, so you can maybe just see this. Call it in a separate. We call it PC. It is giving me the it is returning me the eigenvalue and eigenvector. All right. So, and you see it's the flipped one, not the original one that we have. So now what we are doing is, as you all know, that the eigenvalues give you the variance, and the first principal component is the largest variance, right? So the largest eigenvalue for the covariance matrix corresponds to the first principal component, and it gives you the highest variance. So I can call this eigenval to be equal to variance, and I can call this eigenvector to be principal components, right? So that's what we have done here. So variance, we are calling it we are calling eigenvalue, the first component of get PC function, to be variance, and the second to be PC. All right. So once we have that, let's just see. So this variance and these principal components is given by your PC of C. So variance of you call is this, and PC is if you call this. Okay. So what is the first principal component? First principal component is you are going to take of this array that you have, you are going to take all the rows of the first column, right? So all the rows of the first column. So PC, your PC is all the rows and column 0. This will give you PC1, right? And if you want the second principal component, you can basically print this, print first principal component is this, and the second principal component will be right. And what is the variance along the principal component one? Just see that also. So print variance along PC1 is going to be, so it is going to come from variance ka 0th element, right? So variance I would want and for the second one, we want it to be variance along the second principal component. We want this to be
1.
1, right? So now it will give me everything. The variance along PC1 is 1.88, variance along PC2 is 0. And all that thing, I mean, these two steps that we have done is what is giving him. Fill out this code. It is giving me, it is the very first function get piece is giving me eigenvalue eigenvector of the centered of the covariance matrix, and also giving me the principal components and its variance. Okay. Any doubts so far? Is it all clear? Okay. Right. So we have completed till computing the eigenvalue and eigenvectors. So now let's just see how these principal components look like. So, like to see how these principal components look like. So what do we want to do? So we had this center data set with us. We had the center data set. Now on this center data set, I want to plot PC1 and I want to plot PC2. Okay. So to plot PC1, PC2, I need a vector. I need a point, right? So all I have, what is PC1? I know PC1 is this 0.70, 0.70 is PC1, right? So I need to draw two lines. I need to draw the first line, one line for PC1, one line for PC2. Okay, so how can we do it? Is what we'll see. So I hope you have already seen this slit space command yesterday.
Yes, ma'am.
Yeah. So this length space command is giving you just generating numbers between -2 to 2. So I can call this plot function that we had defined here. I don't know if I run that, but the plot function, if you call plot of x, it will give you this centered data set plot. Okay. Now in this line of the code, I'm generating numbers between -2 to 2. Because my center data set, if you look at it's we are given this axis to be between -2 to 2. So up. Okay, not really, but okay. So here we are generating between -2 to 2. You can increase it if you want. Let's just maybe -3. So I'm going to generate samples. Going to generate numbers between -3 to 3, and I want to plot this x, right? And what is the equation of the line? Equation of the straight line. So what is y is equal to mx, right? This is the equation of a line. Now in this case, what is my m is what we have to figure out. So y is equal to mx, right? So we need to figure out what is this m. That is. So see the principal component. So the principal components PC1 that you had was this, right? It's 0.70, 0.70. Okay. So B by A is what gives the slope of any vector, right? B by A is the slope given by the vector. I hope you all know that. B by
Yes,
A.
ma'am.
Yes, ma'am.
Right? So in this case, it is the second component of PC1 divided by the first component of PC1. Right? So I am going to take like all the rows, but the 0x component. I mean, first let's see what was PCs. So I run it here. So PCs what this, right? This was my PCs that we had obtained. Okay. So for the first, we need to get the all the rows I mean both rows, but the first component of it, right? So 0th component. And out of that, I need to get the second entry, right? This is what we are doing. So PCs, all PCs. This is my PCs, right? So what are we doing? We are taking the PCs and principal components, and we want all the rows. We want the rows and the first, the very first column is what we want. And out of this, I want the second entry of this. I want 0.707. So I will do 1. Correct? So this is my P. And what is my A going to be? A is going to be PCs. You have, I mean, you want all the rows and the first column. First column. Sorry. I mean, first we are finding for the PC1, right? So I'll stick to 0, right? So of 0, I want the first entry, first element, which is this part. And that is given by 0. Okay. So this is what I get. I get 1.00 as the slope of this line that we're going to get. Right. Similarly, if we have to do it for the second principal component, which is minus 0.70 and 0.70, what we will do? We will do PCs. So we want all the rows, and the second column. So it will be given by 1. And of the second column, I want the second entry, which is given by 1. I will divide this by PCs. This follow. This is 0. And of the, sorry, not 0, 1 again, right? 1 again of a 0.
Ma'am, better way is just we can write PC 0, 1, right?
PC 0. Yeah, no, yeah.
Just choosing a element of X and Y column, so it's like
yeah, sure. Okay. PCs 0.
Yeah, that's more direct, but I feel like for understanding like how exactly we're getting it, the way that Ham has indexed it is like easier to get. But yeah, more direct is to like PC1 and then 0 or 0, 1.
Okay.
I guess you need double brackets also now for that if you use that method.
no, it will work without
No,
double brackets also.
Oh, it works. Okay.
it's fine. That's fine. So PC is 0. I want, okay, I want now what? I want second, I wanted second row. No? So I need 1 here, and I wanted the first column, this right? And I wanted first row and the first column, 0, right? Yeah. This will work. So this is what we are doing. This will give us the slope. So that's what we have done here. So when you do PLT dot plot, you must give the X and you need to give Y, right? So Y in this case is MX. So M is given by this and you have X. We have assigned the color to be red and label to be PC1. Similarly, if we did it for PC2, assign the color to be purple and label it as PC2. We run this and this is what we get. Any doubts so far?
Just slope thing is a doubt. Like how slope we are calculating by PC1 by PC2?
Not by PC1 and PC2. So we took a particular PC. So in this case, as I showed here, this was my PCs, right? This matrix. This matrix was my PC. Now, what I wanted is this 0.70 and 0.70 is my PC1. Okay. To find the slope of this, I need the second component divided by the first component. Now this is nothing but a matrix. Okay. Now to get this element, what can I do? So I'm going to look at row 2, which is given
So
by
that impression I got it. Just I was figuring it out like why this.
so B by A. So B by A, right? The slope is given by B by A. So you think of this as A, and you think of this as B. So this is just a vector, right? So A comma B. Now if you have to find the slope, this is given by B by A. So that's why we did this. And once we have done that, I can write y to be mx. This is my m times x. And x is, we have taken in -3 to 3. We have generated x in -3 to 3 and plotting this y, x and y. Okay. All right. So till here it is clear. So how to visualize this? How to get this PC1, PC2? All right. So what can be done is, like whatever we have done can be put in a function, so that if any new data set comes in, you can just call these functions and do the work, right? So in this, here we have done that. So we have put everything in this inside this function, and if you call this function PCX, it will return you eigenvalue and eigenvector, and all the work that we were doing, like centering the data set, finding the covariance, finding the eigenvalues, flipping the eigenvalue by eigenvector, it will do all the work inside, and it will return you eigenvalue and eigenvector. All right. So we'll just run this function, and even the plotting, all that we were doing, like plotting the actual data set, the central data set, and plotting this PCs, is all we have put in this plot function, which takes two input, x and PCs. Okay. So this also, let's run this. Now, if I have a different data set, so see, now if I call, so if I take np dot array, here I'll just take the same example. So 2, 5. I call, if I take this new, and if I take this variance, if I take this covariance, I specify the size to 1000. Now, how do we remember? Like we had also defined the function generate at the very starting. So, yeah, here we have defined this function, right? So let's just, so I can just call this function. So generate new covariance and I'll just call this function x is equal to generate new comma covariance comma n, and it will generate samples from the bivariate distribution. So what do we want to do here? We want to like for this data set, if we have to run this PCA, what will it give? So if I call this x, so maybe variance and in principal component is given by my PCA function is x. This is what we have defined as PCX. I return eigenvalue and eigenvector, and we are calling plus variance plus PCs. Now, if you call this variance and PCs, it will give you, for this set of data point, it is doing all the work of like centering the data set, finding its eigenvalue, eigenvector, and just giving you the variance and PCs. Okay. So I can also call the plot function, plot x species, right? If you do plot x comma x should give you all this thing. So we just increase this. So, right, so this is one benefit that we get by defining the function. Now we don't have to redo all these things again and again. We can just call these functions, speed and plot, and just giving the data set, I can get the all the information that we wanted. Is this clear to here? Okay, got it. Yes. Also one application which we're able to do now. Let me go back to the second part. We'll try to do whatever we can today. Whatever will be left, we'll do it maybe tomorrow or day after. One. Okay. So next is this k-means algorithm. So what do we do in k-means algorithm? Let's just write that first. So in k-means algorithm, what is my first step? My first step is like we randomly assign the data points. We randomly assign the data point as centers. It's the cluster center. Okay. Like this depends on like the very first thing that you will do is to specify the number of clusters, right? So specify the number of clusters you want. Okay. Once you have specified how many clusters you want, then next thing we do is we randomly assign the data points as cluster center. So we randomly pick the data point. Let's say I have a data point of 1000. I will randomly pick 3. If my cluster number is 3, I will randomly pick 3 data point and will assign this my initial cluster center. Now next is depending on we calculate the distance. So next is we calculate the distance of each of the data points. Data points from each cluster. Distance of all from each cluster center. Right? We do this. So once we have the initial cluster centers with us, we assign, we calculate the distance of every data point to each of the cluster centers. Okay. So once we have done this, once we have calculated the distance of all the data points from every cluster, now we will look at based on the minimum distance, based on the minimum distance, we assign
the clusters,
data points to that cluster, right? To that cluster, and we keep on repeating. Then once we have assigned it, plus update the cluster centers, right? Update the cluster centers, and we keep on repeating this. Keep on repeating this process until
Convergence.
uh, reassignment is happening. Right? Okay. These are the steps that to follow. Right. So we'll see all this. So again, we'll look at this for a small data set. So the very first thing we would want is generating the data set, right? So let's just import the libraries. Comprise it. Import the matplotlib. Okay. So again, we are just generating a small sample. So based on like, okay, so just put RNG also here. So RNG is equal to dot default RNG. So you see, we are going back to our bivariate normal distributions, and now we have these three means with us, right? The first mean is -3 is what we are doing. The second is 3 comma -3, and third is 3 comma 3. So these are the three means. So what is the shape of this if you look at? So just after this, we want to see means dot shape is 3 rows and 2 columns. Okay. So we have three data points. We have three centers. So we are starting with a cluster. I mean, we are starting with 3 clustering. Okay. We are assigning K to be 3. So we want 3 centers, and the very first thing we are doing is we have, I mean, -3, 3 comma -3, and 3 comma 3 is the mean we have taken. Now, based on these mu's and this covariance NP dot, so in this case, we are taking the identity matrix. So it's of size 2 comma 2, right? So based on all this data that we have, I am going to generate this data point. I mean, generate the samples from this bivariate normal distributions, right? So we already know how to do this. So we have this. So what we are doing currently is we are generating our samples RNG dot multivariate normal, okay, with these mu's with this covariance and sizes.
Aja, in PCA, we did not use multivariate. We just used 2 dimensions, R2.
No, we used bivariate.
Bivariate, right?
Yeah, yeah.
Can we also do this simulation with multivariate with PCA also?
We have done the same thing, right? What did you say?
Like multivariate in PCA.
Even in PCA we did the multivariate only, right? In bivariate we had taken. You are saying
more than 2.
More? Yeah, you can do that. You can do that. Not a problem. Okay. mean must be one dimension.
Mom, you need to wrap it in a loop and take like
Yeah, yeah.
each here.
Yeah, this is the dimension issue because see, my mu was in it's 3 cross 2. My covariance is 2 cross 2. So we need to run this. So what we have done is we are putting this in x vals. This is another variable, and we are generating the multivariate normal with uh, mu's covariance and size n by 3, right? So what we want currently is, see, we have 3 centers with us. We want to generate samples from 3 centers, 3 means. Okay? And if we are generating a total sample of size 60, then what we currently want is like 20 samples from, let's say, the first center, first cluster, 20 samples from the second cluster, and 20 samples from the third cluster is how we want to generate this. So for that, uh, we have put this in a we have put this in the loop, and what are we saying? Xvals is RNG dot multivariate normal, which means mu i's, right? Covariance and size n by 3. So for every I, it will take for every I. So like for every 3 cross 3, I mean this mu, for every mu you take, it is going to generate a sample of size 20, right? Because it's n by 3 for I in range 3. Okay. So once you have that, once you have this X files, you can just run this and see. Um, So once you have like 20, 20, 20 sample, we want to compile all this in one matrix X, right? Concatenate is what it is doing. So now you have 3 different uh, data set, I mean 3 different matrices that you get in X vals. So each of size 20 cross 60, I mean 20 cross 2, right? And now you want to merge all this into one matrix. That's why we are concatenating, we are using this concatenate, and we are doing the axis to be 0. Remember, like axis is equal to 1 was for if you want to stack it in column wise, right? But we're stacking it here row wise, right? So we are stacking it row wise here, and uh, we are just, let's see if what happens if we do not take the transpose. So if you do not take the transpose, I'm generating a data set of size 60 comma 2. All right. So I mean, this is again n cross d type. So this is not what we want. We want 2 cross 60, right? So I just do the transpose. Right. So we are just first generating my data set. Now, once you have the data set with you, what can we do? We can like plot this to see how it looks like. Like what we have tried to do is for every mean that we have created the data set. So to visualize this, we can do the scatter plot. So plt dot scatter you do. If you do plt dot scatter, what we want x ka 0th component and x the first component work, and plt dot axis be equal to from the that is in the problem axis. Yeah. So you can see now you have generated samples from three. I mean, you can see the three clusters here, right? So this is how my data set looks like right now. Okay. So once we have the data set, what is the next thing that we will want to do? We want to check the distance of each of the data point from its mean, right? So from the cluster center one, now just compute what is the mean of this cluster center, compute what is the mean of this cluster, and compute what is the mean of this cluster, right? So it's not that the mean that we had started with, I mean, where is it? So the very first center, if you look at, it is somewhere between -4 and 4. But this is not the center that we had. This is not the mu that we had used, right? So it's not that the center is, the cluster centers are going to be again the same. So you need to compute this. So you compute the cluster centers of each of these again. And once you have computed the cluster center, now you need to find the distance. Okay. So that we'll do next.
Can you once show the plotting code for this?
Yeah, this one.
Okay,
So
ma'am.
just plot starter x0, x1. I think that should go. Yeah, also. Right. So this is my data set. We saw the data set, and now what do we want to do? We want to now assign. Now we want to find the mean of each of these cluster centers. Okay. Okay. Okay, let's just try how much we can do today. All right. So first we have the data set. Now the very first step is initialization. So how do we initialize it? How do we initialize the centers? We do it randomly, right? So that's what we do here. So we had specified my k to be 3, and I know d comma n is my x dot shape. So what do we want to do? We want to like all the data set that we have. So currently the data set we have taken is of size 3. So we want to look at each of these data set, and we want to choose 3 of that, right? We want to randomly choose 3 of that, correct? This is the data set. What do we want? We want to randomly choose 3 points here, correct? So for that, what are we going to do? We had seen this function rng dot choice, right? For choosing the data, for choosing the indexes, or for getting these indexes, right? Like in case of Bernoulli, we're getting 0, 1, multivariate, we saw 0, 1, 2, and so on. So now here, what we want is, so we had specified, since we can see there are 3 clusters in the data set. So k is equal to 3, and my shape we know is x dot shape. So what we want to have the index, and we'll get this by rng dot choice function. Okay. So we want to look at the all the data set from uh, 0 to n, right? So what will you do? So you will do so I want all the data point and I want the size k. Size will be k and I want the step replacement to be false. Range replacement or replace is equal to false.
Small r.
Very small. Yeah. So if you do this, now it is going to give you free index. Why we did replace to be false is we don't want the cluster set list to be same, right? So that's why we are doing replace to be false. So we have now 3 index that we have obtained out of the 60 data set, 60 data point that we had. Now I have chosen 40th, 41st and 55th data point, right? So now I am going to assign these index as my initial cluster centers. Okay? That's what we are doing here. So my mu, now mu is going to be x of all the rows, but with these indexes. And what are these indexes? These indexes 40, 41 and 55 is what you want. Okay, so that will give me the initial mu. All right. So once you have this initial mu, see search chart. Or maybe I think we can stop it here today. We'll continue tomorrow. That is okay. So far what we have done is in clustering is we have initialized, we have generated this data set. We saw there are 3 clusters in the data set. So now once we have 3 data set, we want to initialize. We have just done the random initialization. So that's all we have done so far. So what I will do is, so after this initialization, you need to do the assignment and complete the cluster centers again. I will share this collab with you. You go through this collab, and tomorrow, if you have any doubt somewhere, we can just take those instead of going through this whole thing.
Ma'am, what will do tomorrow?
Sorry.
Ma'am, what will be the agenda of tomorrow?
Okay, so tomorrow we are going to look at regression.
Ma'am, so is it the KNN model is used in this question for k-mean clusters and all?
KNN is different, no? KNN is K nearest neighbor.
Yes, ma'am. So
This is
will it be
K-means
used in
clustering.
these types of questions for classification type?
Oh, I didn't understand your question. Can you repeat?
KNN is classification model, right?
Classification model, right? Right? Yeah.
So it is used for these type of model where we have clusters, K clusters, so something related
Okay,
to like that.
so K means clustering is see, K means clustering. You have the data set with you, and from there you are trying to figure out some information, right? So here we did not have label with us. We only have the data set. We had the X. It's an unsupervised learning algorithm, right? Once we have the data set, now we can figure out some information about it, right? And that's for that we are doing this image clustering algorithm. Now KNN is different, right? So KNN is what you do is you look at you specify the K, and for every data point of whatever K you specify, you are going to look at those many neighbors around your test point, right? And the majority of the labels that you get in the neighborhood, that is what you're going to specify the label as.
Yes, ma'am.
These two are two different algorithms, not the same.
Okay.
So I'll stop here. So I will share the collab. You can go through it and just run these and see if you face any issues anywhere. We'll take that tomorrow or day after tomorrow. There is time. Okay. So I will share the collab.
Are you sharing the collab right now, ma'am, or after that?
No, not right now. After the session, I will just put it in the same sheet that we had.
Okay. Okay.
Thank you.
Ma'am, tomorrow which module we'll see? Which algorithm?
Tomorrow